Okay, so I promised that I would do problems 16 and 19 from Fraleigh for you. I'll at least start with 16 and send this video out, and then hopefully I'll be able to get on to 19. But I'm a little pressed for time today. So what happens in 16? We're given that we have z with ordinary addition, and then we have z with some undefined operation. And we're given a map that's defined. It's called phi. And phi takes something from here, a number, and maps it to n plus 1. And that's in here. And we want to define, we know what phi is, but we want to define star, so star is unknown. So we want to define star so that it's an isomorphism. That's the tricky part. You guys can check one-to-one and onto yourselves. But the tricky part for this one is defining star so it's an isomorphism. So what would it mean for star to be an isomorphism? So if star is an isomorphism, then we should be able to take the sum of two elements in Z, so m plus n in Z, and that should be equal to, we should be able to apply phi to a sum of two elements. That should be phi of m star phi of n. That's the homomorphism property. If it's a one-to-one and onto map and satisfies the homomorphism property, then it's an isomorphism. So I did this one way in class, but apparently it was not very satisfying. So let me try another tack. And let's just try some examples. We know what the elements of Z look like. We know how to do addition. The only thing we don't know how to do is star. So let's try some numbers. So let's try, very simplistically, let's just try phi of 4. So phi of 4 is equal to 4 plus 1, which is 5, right? And phi of 7 is equal to 7 plus 1, which is 8, if I've got my math correct. And now let's try breaking these up into pieces. So we know 4 is equal to 2 plus 2, right? So we already know that phi of 4, or phi of 2 plus 2, same thing, is equal to 5. But if this is going to be an isomorphism, it's also got to be equal to phi of 2 star phi of 2. And I'll bet now you're starting to recognize why the isomorphism property is as it is, right? It shouldn't matter how I represent 4 when I map it over, right? Phi of 2 plus 2 should be the same as 4. So anyway, let's continue. We do know what phi does. We don't know what star does. We know what phi does. Phi of 2 is 2 plus 1, right? Star 2 plus 1. So that's 3 star 3. Well, notice star can't be regular addition. Why not? Because 3 plus 3 is equal to 6, and 6 is not equal to 5. So it can't be regular addition, but on the other hand, it's pretty close to regular addition, right? 6 is pretty close to 5. So let's try another number and see if we can tease out a pattern. Well, phi of 5 plus 2, well, that's 7, right? So phi of 7 should be 8. We've already done that. But if it's going to be an isomorphism, it should also be phi of 5 star phi of 2, which is 6 star 3. Now once again, can't be regular addition, but notice 6 plus 3 is equal to 9 is just one more than 8. So I'm going to conjecture that m star n is equal to, well, almost regular addition, m plus n, but it always comes out one too many in terms of making it an isomorphism, so I'm going to say m star n is equal to m plus n minus 1. And I'm going to test my conjecture. So let's do phi of m plus n. Well, we know that phi of m plus n is just m, oops, I don't know why that wrote down there, is just m, what is wrong with my pen, m plus n plus 1. Now if it's an isomorphism, if phi happens to be an isomorphism and we've chosen star correctly, or if we've chosen star correctly to make phi an isomorphism, then phi of m plus n should be phi of m star phi of n. Well, we know what phi does. That adds 1, so this is m plus 1 star n plus 1. And we've now decided on how star is going to operate. So star just subtracts 1 from the sum. So we go m plus 1 plus n plus 1 minus 1, which is m plus n plus 1. Aha! It works. It's an isomorphism. So star defined in this way makes phi an isomorphism.